Now we're on to the chapter of gases, liquids, and solids. And honestly, the majority of the chapter is going to be dealing with gases, and that's where all the calculations come in and all the gas laws. But before we get into all of that, there's a bunch of theoretical stuff we need to get into. So if you look at the what you need to know list, the first thing on the what you need to know list says read through the kinetic molecular theory. So I've got the 5 key statements of the kinetic molecular theory on the board. I'll go through them with you guys, and then we will talk about the table that differentiates between the properties of solids, properties of liquids, and properties of gases. And once we do that, then we'll be ready to get into talking about gases and pressure and the gas laws and all of that. So first things first, kinetic molecular theory. Hopefully you can see this. I'll bring it in a little closer. You can expand it out at home and hopefully see this. Okay, so the key points of the kinetic molecular theory. Number 1, matter is composed of tiny particles. What do I mean by tiny particles? Ions, atoms, molecules. Matter is composed of those, and those aren't going to be changing. Okay, so yeah, they can react with each other, but that's what matter is made up of. Okay, particles move constantly. What does that mean? It means that no matter what state of matter, whether it's a solid or a liquid or a gas, there's always some type of vibration. Some matter moves around like crazy, like gases you're going to see are moving a lot. They have a lot of kinetic energy. But even a solid, like this calculator, the particles within the solid are slightly vibrating, okay? So there's some kinetic energy. Not a lot in a solid, there's a lot in a liquid. Particles interact with each other. So particles can interact with each other, and that interaction, that attraction, that electrostatic attraction between particles, that's what's considered the potential energy, okay? As the temperature increases, kinetic energy increases. What does that mean? Well, as you increase the temperature, your molecules are going to have more kinetic energy. They're going to move faster, okay? And then you're going to see things expanding, especially with the gases, okay? And then finally, particles transfer energy. So there's a law that says the law of conservation of energy. So basically, one particle can collide into another particle and transfer energy from one particle to another. These collisions are called elastic collisions, and this transfer occurs because it's this, and it makes this one move. So there's the collision thing and the transfer of energy. All right. So those are the 5 main things. Read through them. I sort of gave you an idea about them. That's what you need to know. Okay. Now, 3 states of matter: solids, liquids, gases. We've already discussed this in previous chapters, but let's go through it one more time with a little bit more information. Okay. So solids all have a definite volume, a definite shape, a high density, small compressibility. What is compressibility? That means that you can squish something and put it in a smaller volume. Well, solids, you can't really do that. You can do that a lot with gases. You can't really do that with solids or liquids, so we call it small compressibility. The less technical word for compressibility is squishing it into a smaller space, okay? Small thermal expansion. What does that mean? It means that if you heat something up, will it expand? Well, with solids and liquids, they expand, but not very much, okay? So small. These are terms we also saw before in previous chapters. Solids have high cohesive potential forces, okay? And they have low kinetic disruptive forces. So kinetic forces are the disruptive forces. So solids tend not to go all over the place. They're just staying where they are. So they have cohesive forces, and they have very little disruptive forces. The opposite is true for gases. Now, if you take a look at liquids, what I did was I checked off the things that liquids are similar to solids. So liquids also have a definite volume, but they don't have a definite shape. Liquids also have a reasonably high density. They also have small compressibility, just like solids. They also have small thermal expansion, just like solids. But here they differ. The disruptive and cohesive forces are about the same in a liquid. Now, with a solid, we said the cohesive are considerably more than the disruptive. The potential forces are more than the kinetic forces, but with a liquid, it's pretty much even. Okay, now what about a gas? A gas differs in pretty much everything than a solid. A gas has an indefinite volume. A gas has an indefinite shape. A gas has low density. A gas has high compressibility. A gas has not bad, medium thermal expansion, because gases will expand. A gas has very low cohesive forces, and a gas has high kinetic forces. Okay, so that compares the solids, liquids, and gases. So all this theory stuff, the kinetic molecular theory, and these things are potential theoretical questions, so you should know those. All right, so we're ready to move on to gases, and the next thing on our what you need to know list specifically talks about pressure. Now, we've already measured in this class, we've measured mass, we've measured volume, we've measured temperature, and we've talked about all of those, but we haven't talked about pressure and what units of pressure we're gonna talk about. So let's focus now on units of pressure. You probably heard of some of these units. First unit is an ATM, which stands for atmosphere. Another unit is millimeters of mercury. This is millimeters of mercury. Sometimes you'll see it as inches of mercury or centimeters of mercury. There's also torr. The guy that invented the barometer was Torricelli, and he named the unit of pressure after him. So torr comes from the scientist Torricelli. There's also a PSI, which stands for pounds per square inch. Square inch. And then there's also a Pascal. And I'm going to give you the conversions so that you learn how to convert between all of these. But these are the units of pressure. So if you see any one of these units in a problem, you know that they are talking about pressure. Pressure. What is pressure, by the way? Pressure is actually force per unit area. So think of the atmospheric pressure as the atmosphere pushing down on you, okay? Pushing down on the barometer, pushing down on whatever, okay? So pressure, the definition of pressure is force per unit area. And the units that we're going to use are atmospheres, millimeters of mercury, torr, PSI, and Pascal. Pascal is the SI unit for pressure. I think in this class we'll probably be focusing on these guys the most, but you should also know this. You should know all of them. And then I'm going to give you the conversions. And then in the next video, we are going to do the math so that we can convert one unit to the other. So these are things you should know. 1 atmosphere is equal to 760 millimeters of mercury. So put this in your notes, guys. And always think of this zero as a significant zero, because when you're reading it off of a digital barometer or off of an actual big barometer with mercury in it, that is considered a significant zero. So don't try to limit the sig figs here to 2, it's 3. 1 atmosphere is also equal to 760 torr. So what does that tell you? It tells you that a millimeter of mercury is exactly the same as a torr. All right, so 1 torr is 1 millimeter of mercury. All right, 1 atmosphere is equal to 14.7 psi. So 1 atmosphere is 14.7 pounds per square inch. And then finally, 1 atmosphere is equal to 101,325 pascals. Okay? Many times they'll use kilopascal instead of pascal, so it would be 101.325 kilopascals. Okay? Good. All right, so in the next video, we'll actually do some conversions using dimensional analysis using these conversion factors. And then we'll get into the gas laws.